and welcome to video 3 under power quality unit 4. So far now we had an introduction about what are harmonics. We have seen that harmonics are integer multiple of fundamental frequency. Ideally the wave shape must have a single component of harmonic, that is first harmonic. However, because of nonlinear load there is a harmonic distortion in the wave and it becomes non-sinusoidal. It is important to note here that although the wave is non-sinusoidal, it is periodic. So the periodicity is maintained by a non-sinusoidal wave, although there is a sinusoidal nature. So this is the difference between other power quality parameters like instant or unbalance or interruption and harmonic wave, because other waves may be aperiodic, non-sinusoidal aperiodic, but the harmonic wave is non-sinusoidal periodic. Therefore, it is possible to apply Fourier series. As per Fourier series, the aperiodic wave can be resolved into number of sinusoidal waves, or in other words, we can say that if the non-sinusoidal wave is there, then we can resolve it into the number of sinusoidal wave. So that is as per Fourier series, which will be going to study later. Now we have seen that harmonics are controlled by electronics, and there are electronic devices and circuits which are nothing but nonlinear loads. So because of nonlinear loads, number of harmonics are generated and they cause different detrimental effects. We have seen that how the equipments are affected by harmonic distortion. We have seen that the capacitor leads to failure, burning, overheating because of harmonic problem. Transformers, cables, transmission lines, bus bar, protective relays, meters, and number of equipments are affected by high order harmonics, and we have seen that how the high order harmonic will be causing effect on these equipments. Then we see that what are the maloperations. So when the polluted signal is applied to any device, then it starts behaving erratically. For example, numeric relay will give unnecessary tripping pulse, which is not desired, or whenever there is no fault because of harmonics. Because these equipments are very sophisticated and they are designed for low order harmony. They are designed for, sorry, sinusoidal wave. So when this wave is not sinusoidal, they will take shape of maloperation, which will result into lot of chaos, maloperations, etc. Then we have also studied that what are the effects of nonlinear load, what are the maloperations taking place because of harmony. So as we can see here, at harmonic 1, the wave is purely sinusoidal, but as it goes on increasing up to harmonic 25th, it becomes a typical approximated square wave. So this square wave may be very harmful to the sophisticated devices which are there in the system. Now we have seen about capacitor that there is a failure of capacitor which leads to lot of effects which are providing, we are providing capacitor for power factor improvement and for improving voltage profile, but because of PQ analysis there will be failure of capacitors because of high order harmonics. So if you consider to be number of equipments, number of resources, then it can be said that about 42.3% failures, problems occur because of capacitors, because of harmonics to the capacitors. So in this way we can say that these problems can be attended by mitigation of harmonics. Then there is a problem with series inductors. Again, series inductor is a power quality improvement device. So 38.5% problems are observed with respect to series inductor. Means if the harmonics are more, then the probability of problems is 38.5% of the total equipments that are attributed to inductors. Then general equipments like lightning arresters, circuit breakers, meters, etc. So they are also affected to the tune of 17.3%. And all other remaining parameters, they are about 1.9% of the total. So in this way, this indicates that the harmonics are causing lot of problems to the equipments, all types of equipment like substation equipments and improvement equipments. Like we have seen that failure of capacitor banks takes place because capacitors provide low pass impedance to harmonic circuits, harmonic currents. Current will have tendency to flow to the low path, that is capacitors, and there will be overheating and failure of capacitors. Then there are increased errors in energy meters. Energy meters are provided for accurate measurements. However, this purpose is defeated if the harmonic disorder is there. Then there will be protection system, as we have seen. Electromechanical, static and numeric relays are also affected because of harmonic problem. And we have seen that at Hinjwadi MIDC area, there is a frequent tripping of lines because of erratic behavior of numeric relays, which are based on the inputs received from nonlinear sources. Then inductive interference, we studied last time that how inductive interference takes place with neighboring communication network. That is in telephone circuits, there is a lot of noise and distortion because of this type of equipments. Then there is a tripping of transformer or on smaller load or no load. I can give you example of Mundwa substation, which is in the vicinity of nonlinear load devices like Bharat Forge and Kalyani Steel. And in that area, there was a undue tripping of transformers. Without any reason, the tripping was there. Then there are fire hazards. If more current flows through any device, then it is likely that there will be fire hazards and resulting into burning and loss of revenue. Then T&D losses are also increased because of incorrect reading. Then overrated neutral wire. The neutral wire gets overrated because of triplen harmonics particularly, and it can be mitigated by providing zigzag transformer or you mean to say zigzag or any other type of mitigation device. There is a failure of cable insulation, frequent breakdown because of harmonic current flowing through the insulation. So to control these limits, the statutory bodies like IEEE, MACB, IEC has given certain guidelines. As per these guidelines, we can say that THD, that is total harmonic distortion, is the basic parameter for giving limits of harmonics. So it is 5% of IEEE as per IEEE, 3% as per MECB, and 1.5% as per IEC, that is International Electrotech Commission. However, generally IEEE standards are taken into consideration and the THD of 5% is usually allowed. Now this depends on ISC by IL ratio, which we'll be going to study later. So it is ISC by IL ratio which will decide what percent of harmonics is allowed. So 5% is taken as a notional, but however it is IC by IL ratio that decides the percentage. Coming to voltage harmonic distortion level, it can be said that for MECB standard it is 3%, as per IEEE it is 5%, as per IEC it is 1.5%. So in general, IEEE standard of 5% is taken into consideration as a permissible limit for voltage distortion. Then coming to individual distortion, there is a 1% in all the cases of individual distortion. In case of IEC, 1% for odd harmonics and 0.5% of even harmonics components are taken in consideration. Coming to voltage, as per MECB standard, 1% voltage harmonics is allowed. As per IEC, again 1%, and as per IEEE, again 1%. So these limits are always followed, are to be observed. But one thing I have to tell here that THD is not the parameter now to decide the limits. Now it has become TDD, that is total demand distortion. So we'll come to that later in our subsequent videos. Till that time, we'll stop here and we'll continue with video 4 later. So thank you very much for watching and patient listening. Thank you very much.